knowing that we had, usually when we have the second day of inverses, we don't have 10 days in between. So this was just a little review for you about domain and range. Notice that this particular relation, remember a relation was just any set of ordered pairs. They didn't have any special rules about it. Any set of ordered pairs is a relation. So we only have 4 ordered pairs in this relation. Domain is a set. So notice Mahendra put the little curly profile there to indicate it's a set. The range is a set. And these are the 4 elements in the domain, and these are the 2 elements in the range. So it's very important that you make sure you don't have parentheses here or brackets. It's the little indication for a set. It's a -1. -1. Okay. -2, -1, 1, and 2. All right. Any other questions about that?
Is it always like that?
What?
You always have the little squiggly?
Yes, anytime you want to talk about a set, yeah. Okay, but if you want to talk about an interval where something's increasing or decreasing, that's where you have your parentheses. No, the parentheses, yeah, because our book defines it as open intervals. Okay, so if we're talking about where something was increasing or decreasing, you put it over the intervals. But when you talk about domain and range, the most important thing for you to remember is you're always talking about a set of numbers. Sometimes it's an infinite set, Ramses, and sometimes it's finite. In this case, it's finite. Okay. No, okay, so let's talk about the reverse, the components of each ordered pair, and writing the resulting relation. Can you get that door for me, Stephen? So all we did here was reverse the outputs and the inputs. And so notice now that what was originally your range becomes your domain. And what was originally your domain, should become the range. So we got a little problem here because the original domain had 1, 2, 3, 4 different inputs. So that means our range, when we swap these, should have 4 different outputs. So let's see. Here's our reverse. We got a -2 and we have a -1. So we've got to put the -1 in there. So let's erase that. So we have -2, -1. So we got the -2, the -1, a +1, and a +2. Okay. So when we create an inverse, we swap the outputs and the inputs. All right. The domain and range. Up, Molly. Yes. So the domain is squiggly brackets 1, 4, because it's a set. Always keep in mind it's a set. And the range is -2, -1, 1, and 2 is a set. Okay. So say, for example, we knew that this was actually a line on that line. It's not on a line. Right, no, I know. I'm saying hypothetically. Yeah. For writing the domain and range, the reason you're doing the squigglies is just that it's 4 points. You don't know if there's, what I had written was like the domain was -2, 2 in brackets because like the lowest x value is -2 and the highest x value. Okay, so let's talk about that briefly for a minute. Because this relation only has 4 points. So in other words, if you were to graph this, you would have -2, 4 right here, right? -1, 1. 1, 1, and 2, 4. Okay, so this is the only thing. If you say the domain for this goes like this, then what you're saying is that this interval from -2 to 2 defines the domain, which means that every single point on the number line from -2 to 2 has an output, and it doesn't. It doesn't matter whether this represents this set. An interval, when you put it in your homework, represents a set of numbers, and the set of numbers would be all the numbers less than or equal to 2, or in this case, just, what did you have, parentheses? I had brackets. Okay, all right, okay, that's okay. Yeah, okay, I understand. I'm helping Ramses understand. Okay, so when you write something like this, Ramses, you're saying that the domain is all the numbers, which is an infinite number between -2 and 2. And therefore, these points would have to be connected like this. You see? Because it would have, for every single value of x on that domain, you'd have an output. Whereas we only have 4 elements of our domain, -2, -1, 1, and 2. And we have 4 outputs, only 2 different outputs. So the domain here is just these 4 elements. If it looked like this, it looks like your basic parabola, x squared, right? And you could say if it continued to infinity like this, then you could say your domain was -infinity to infinity. It could be all real numbers, but it's only these 4 points, and that's what's.
Would I have been correct though? If say it did go to infinity, it just stopped at 2, 4 and -2, 4, and if it was a line in between.
If it was, yes. So if we decided that we were just defining the values from -2 to +2 and connecting them with that parabola, then it would be -2 brackets, -2 comma 2 brackets. Then that would be the domain, because there is a value for everything in between, you see? So that's the difference, okay? So this would, if that point was on there, this would be -2 to 2. That would be the domain if it was connected with a parabola. Okay, is that clear now to folks? Okay, it's much simpler than what you've been working with for like your projects and things like that. It's doesn't have any, like, there's not a lot going on there. It's just 4 points. Okay, so then when we reverse them, what was the domain becomes the range, and what was the range becomes the domain. So now the 2 questions of the hour really, in terms of what we're going to be focused on today, is D and E. So we're wondering, if I take this relation, which is just these 4 ordered pairs here, and I reverse them, is this inverse a relation or is it a function? Okay, so if we look at just these 4 points, what was the basic definition of a function? For each input, there's exactly 1 output. So if we look at these ordered pairs and we look at 4, if 4 goes into our machine, what comes out? 2 on -2. So that's a big problem. We can only have 1 output. It's just a relation. It is not a function. So its inverse is a relation. It's not a function. And therefore, let's take a look at E. A function whose inverse is also a function. So here's a function. Right here, we started off with this function. Its inverse wasn't a function. So, and now we're going to see why. A function whose inverse is also a function is called one-to-one. So this function that is defined right here, this is not one-to-one. It's not one-to-one. And the reason is I have different inputs. Let's take a look at -2 and 2. -2 and 2 are different inputs, but they bring me to the same y value, which makes it a function, but it's not one-to-one. That's right. Every input must have a different output for you to be one-to-one. So every input in your function must have a different output. To be one-to-one. Okay. Doesn't mean it's not a function, because y equals x squared, f of x equals x squared is a beautiful parabola. That's a function, but it's not one-to-one. Because if you look at your parabola, every value of x to the left of 0 is different than every value of x to the right of 0, but this has even symmetry, so it doesn't have different outputs for different inputs. So this is not 1-to-1, which means that your basic parabola does not have an inverse function.
Would it be connected to the one zero then? Yeah, one in other multiple outputs.
Well, they actually don't give a name for that, but that wouldn't be too bad, Ramsey, right? That if it had 1 to 2 outputs, right? Yeah, yeah, that might be an interesting way to help you remember that. Yeah.
Could you also not have a, oh, no, I guess I was going to say with this,
Nick's bringing up an interesting idea. So let's take a look at Nick's idea. Because he's saying, wait a minute, wouldn't the inverse of squaring something be the square root? That's what a lot of people think, right? So here you have your parent parabola, f of x equals x squared. So why couldn't the inverse of this be that? And the reason is this, I could put an x in here and out would come one value, but it's only the positive value. So in other words, if we take a look at f of x, let's define some, we know that the domain for f of x for the function f is all real numbers. But if we just take a look at a couple of points like this, which is what we were doing originally, okay? And we say, okay, if we put a -2 in, out comes a 4, so this is a function. But if we try to look at the inverse function says the positive square root of x, right? So if we put a 4 in here, so if we take the output and it now becomes the input into my inverse function, the square root of 4 is 2, because this says find the positive square root only. When you see that symbol, it's only asking you for the positive square root. And we know that from our original function, there were 2 values that gave us 4, both a negative and a positive 2. And you can't define the inverse function to be this. You can't do that. You can't say this is a function because you put in an x value and look what you're saying. I got 2 different y values. No go. So this does not have an inverse that's a function unless you do something. And there's something in mathematics that we do, and that is we restrict the domain of this. If we say f of x is x squared for x greater than or equal to 0, then what happens is this part of your parabola disappears. This is what f of x equals x squared for x being greater than or equal to 0 would look like. Now this is the inverse, because this function says tell me all the positive square roots of x. So now when I put 0 in, I get 0. When I put 1 in, I get 1. When I put 4 in, I get 2. When I put 9 in, I get 3. Okay, so these are the original values, and this is what the inverse looks like.
those are both 1-to-1.
Yeah, they're both 1-to-1. Yeah. So if you look at this original function, let's make it red. If I, whoops, I'm going ahead, I'm giving you the answer. Right. So anyway, if you have a function that is not 1-to-1, you can find, sometimes you can find an inverse function by restricting the domain. Okay, so anytime you have something that has even symmetry, that's, you would have to restrict the domain so that you're only looking at one part of it. So let's continue with this. A lot of good ideas came up in that preview exercises. Thank you for all the questions. Okay, so does every function have an inverse function? Well, we just saw that we had a function in the preview exercises, and the inverse relation was not a function. So one of the things we want to determine today is how can we tell whether something has a function that's an inverse that's a function, okay? How can we look at a function? Can we do a visual test? And then if we find the function's inverse algebraically, how do we test to see if it truly is the inverse? So that's where we're going today. So to answer this question, let's examine 2 functions. Our first function is f of x equals x plus 1. What name do we give to a function like that? F of x equals x plus 1, other than Nick. linear, right? So this is a linear function, linear. Okay, so we know that's going to look like this. It's a straight line. What else do we know about this straight line? It goes through 0, 1, and negative 1, 0, and it has a slope of 1. So this is our function f. Does every single input have one and only one output? Yes, it passes the vertical line test. It's definitely a function. Do different inputs have different outputs when you look at this? Do different inputs have different outputs? Okay, can you give me two different inputs that have the same output? Yeah, so if I go over here to x, I come down here as y. If I go over here maybe to its opposite, y is different, right? So do different x values have different y values? So some of you are saying, yes, I still had a very strong no somewhere over here on the left-hand side of the room. Okay, do you want to change it? You want to change it?
Yeah.
Okay, so yes. So what do we know? Is this function f going to have an inverse that's a function? Yeah, okay. It's going to have an inverse that's a function. Another way to tell, we're going to see one way in a minute, but is this function, as you move from the left to the right, is it always increasing? Any function that is always increasing over its domain, as you move left to right, will have an inverse function. Same thing is true if I just reverse the slope on this and make it negative 5x minus 6. Then it would be a line that has negative slope. Any function that's always decreasing will have an inverse function. So sometimes if you know what the graph looks like and you say, this function's always increasing or it's always decreasing, it has an inverse function. All right, so that's worth writing down for yourself. Okay, so here are 4 possible solutions for this function. Here would be 4 ordered pairs that solve this equation. If I put negative 2 in for x, out pops a negative 1, vice versa. So here are 4 ordered pairs. If I reverse the components, I get this. So for different outputs, I have different, for different inputs, I have different outputs. So this means the function is 1-to-1. Okay? Now, let's take a look at our parabola here, which is a quadratic function. Okay, this is our basic function x squared shifted to the right 1 unit. So this function would be our basic parabola shifted to the right 1 unit. So it would have 1, 0 for its vertex. It would still go through 0, 1. Okay, so there'd be a point over here, and over here, what would be the corresponding point to the right? If I go 1 unit to the left to get to 1, what would be the value of that point right there if I have 2, 1, right? So you can already see that I have different inputs bringing me to the same output, which means when I reverse it, I'm going to have the same output giving me two different, I'm going to have the same input giving me 2 different outputs. It won't be a function. All right, so you can see here are 4 solutions to this equation. And then when I reverse the inputs and outputs, notice that 4 brings me to negative 1 and 4 brings me to 3. No go, that's not a function. So this function, certain inputs produce exactly the same output. So G does not have an inverse that's a function. So here are 2 different, totally different graphs. One's linear and one's quadratic. We noticed that in this first one, it's always increasing. And look at this quadratic. From the interval of negative infinity to 1, this thing is decreasing. And then from 1 to positive infinity, it's increasing. So it fails at that test of always increasing and always decreasing. So that's one way, okay, you can tell. All right, and then the other way is right here. We have a visual test. Here I've graphed both functions on the same set of axes, and now we want to know if we can look at the graph of a function and tell if it has an inverse. So notice you can barely see it, but you're always supposed to label your graphs. This has a little G there, and this has a little F right here, but it's barely noticeable. All right. So G is this parabola, and F is this straight line. So one of the visual tests is to draw a horizontal line, which is y equals 4, on the graph. So let's draw the horizontal line straight through y equals 4. So let's do that. So here's y equals 4. I'm going to draw a straight line right through there. Let's pick it up a little. There we go. I didn't make it straight. Come on. There we go. It's close enough. I can do better. Let's get rid of that. Let me try it again. All right. Oh no. Oh no. I did worse this time. All right. I'm trying to get it straight. There we go. All right. So there's the line y equals 4. It's a horizontal line. And so now the question is, how many times does it intersect the graph of F, which is our straight line here? How many times does it intersect it? Once. And what's the point where it intersects it? Well, I know my y value has to be 4, so my x value must be 3, because 3 plus 1 is 4. Okay, so it intersects it once at 3, 4. How many times does a line intersect the graph of G? Twice, okay? It intersects it at -1, 4, and it intersects it at 3, 4. Okay. So there you go. It's a function. For different inputs, you have unique outputs, but once you reverse this same output will have, this same output here will become the input, and it will have different outputs. So there's a visual test for whether a function has an inverse function, and that's what we call the horizontal line test. If I take an infinite number of horizontal lines and go up and down this graph, then if at any point it hits your graph in 2 points, no go for an inverse function. And so you can clearly see now that for everything that's always increasing or decreasing, a horizontal line's only going to touch it in one spot. Okay, so
it's a quadratic function. It's not.
That's right. It will never have an inverse function unless, Ramses, you restrict the domain. So if I took this parabola, how would I restrict the domain of this parabola G? So right now, G of x is x minus 1 square. How could I erase this parabola and therefore restrict its domain so it would have an inverse function? Greater than or equal to 1, right? So if I take away this part of the parabola right here, all the way down to its vertex, then it's always increasing. It would have an inverse function, because I'd be looking at the positive square root of x minus 1. Right? Or it could be increasing or decreasing. In other words, I could restrict my domain, let's call it h of x, to be this, Nick, x less than 1 or equal to 1. So I would take this part away.
But it wouldn't be like to the y-axis. It wouldn't be like.
No, it's so.
Then it's like increasing.
Right. Okay. So the horizontal line test, folks, that's our key to whether something is one-to-one. The idea of one-to-oneness means you have an inverse function. So if it passes the horizontal line test, it has an inverse, that's a function. So don't confuse horizontal line test with vertical line test. The vertical line test tells us whether or not you have a function to begin with. Okay, so now the only thing we haven't done is often classes will start just with how do you find the inverse of a function algebraically, and then how do you test it? Well, we've learned how to test it. This is the one I told you to put big stars around last Wednesday, that to test whether two functions are inverses of each other, we compose them, we change their order of the composition, and if they both bring us back to x, then we know they're inverses. So we'll make sure we practice this today. So if I ask you to find the algebraic inverse of this function, f of x equals 5x minus 6, first you should visualize or pull out GeoGebra or pull out a graphing calculator if it's complicated to see if it's 1-to-1. Well, this is a straight line. It's always increasing, so we know this is 1-to-1. So yes, this is 1-to-1, and if we wanted to, we could put a little picture of this. 5x minus 6, so it goes something like this. Okay, so this would be f. So it's 1-to-1 because it passes the horizontal line test. So we know it has an inverse function. An inverse, that's a function. So now we want to find it. Okay. Well, your book uses this strategy called switch and solve. Okay, switch and solve. That's what they call it. And we're going to start off by replacing f of x with y. That's our first thing. And since we know the domains and the ranges change spots, we're going to swap the x with the y. So we're now going to call this x equals 5y minus 6. And we're going to solve this for for y. Okay? So that way it will undo everything. So we talked about on Wednesday that when we undo something, the last step that was done is the first step we undo. So we want to undo, if we want to solve this for y, we want to undo the subtraction of 6 by the inverse of that, which is to add 6 to both sides. Okay. And now what's really important is that you put the x plus 6 in parentheses. Anytime you have more than one term and you're going to end up dividing or multiplying it, you want to keep it in parentheses before you multiply or divide it. And then the last step here is to undo the multiplication of 5, which is to divide both sides by 5. So this now becomes my inverse function. So to solve for y equals x plus 6 over 5. And then to put it back in functional notation, you take your y and you substitute f inverse of x. Right? So I'm just going to change this to be f inverse of x. So that's what I think is my inverse function. Now you could check it out with some numbers if you want. But remember, taking specific numbers will only give you an idea if it's inverse. It won't prove it. So you could start by saying, what if x is 2 up here? If x is 2, then my output would be 4. 5 times 2 is 10, take away 6 is 4. So you could just, off on the side, try something like that. So that's 2, 4. Now you should be able to put this output into this function, its inverse, and come back to 2. So let's see, if I take 4 and I now put that into this function, 4 plus 6 is 10 divided by 5 is 2, you think you might be on the road to seeing that this is the inverse. But to verify it or prove it, you must do this. So let's do these in 2 different orders here. First, I'm going to put my inverse function into my function f, and then I'm going to change the order of that composition. Oops, change the order.
Is that like reading the inverse function of f, of the function f? Reading that like f outside of
Yeah, this says that my function f tells me up here, Ramses, my function f tells me whatever I put in here, I multiply it by 5 and subtract 6, right? So now what I'm going to put in to f is this thing called f inverse of x. Okay, so I like to do it with colors versus first. So I'd like to take a look at this. Here's my blob. That's my input. So my f function tells me to take my blob, whatever it is, and multiply it by 5. 5 times my blob, take away 6. So now what's my blob? My blob is f inverse of x. And I think f inverse of x is this thing called x plus 6 divided by 5. So I replace my blob with the algebra. And now I have to see, does this give me x? And if it does, I have half of a smiley face. So let's see. My 5s cancel. Plus 6 minus 6 goes to 0. X is equal to x. So I have the left side of my smiley face. Okay. Now I have to do the right side of my smiley face. So now I reverse the order of my composition. Now I'm looking at using f of x as the input into what I think is its inverse function. So what does the inverse function say to do? My inverse says to take my blob, add 6 to it, and then divide the whole thing by 5. So let's do that. So it says take my blob, add 6 to it, and divide the whole thing by 5. That's what it tells me to do. So let's replace the blob now. Blob is f of x. So f of x is 5x take away 6. That's my blob right here. I'm going to add 6 to it and divide by 5. So let's see what that gives us. This negative 6 and the plus 6 gives me 0. That gives me 5x over 5. That gives me x. X equals x. Now I can complete my smiley face. Okay, so now you have proven that these two functions are inverses of each other. And that is the only way you can demonstrate, verify, or prove that two functions are inverses of each other. Hint, hint, hint. Okay, for Friday. Any questions on this? Okay, now you're going to be looking at a series of different things for graphing input, for graphing inverses, and also a way of looking at inverses. I have these mirrors on your table. So when you get to number, let's see, I don't have a packet anymore because I gave my last packet away. But when you get to number 4, before you start sketching the inverse, call me over because I want to show you how to use these mirrors. It's really neat. Okay, I'll be happy to help anybody